You ever wonder if there are some things we just can't know for sure? Today, we are diving headfirst into a discovery that totally shook the foundations of logic and math. We're talking about Kurt Gödel's absolutely mind-bending incompleteness theorem. It all boils down to this one massive question. If something is true, can we always prove it? For centuries, some of the smartest people on the planet were chasing after absolute certainty, and they were pretty convinced the answer was a big, loud yes. So to really get this, you have to picture the early 20th century. Science is just exploding with new discoveries, and at the core of all of it was this hunt for a rock-solid foundation for all knowledge. The ultimate dream was to create a perfect, unbreakable logical system. And where did they turn to find this perfect foundation? You guessed it, mathematics. It was seen as this pure, perfect language. For a field like physics, math wasn't just a handy tool, it was the anchor of certainty. It was supposed to be the final word on reality. Now, the guy leading this charge, the champion of this grand vision, was David Hilbert. You can think of him as the ultimate optimist of mathematics. He genuinely believed we could build a complete system of logic with absolutely no gaps and zero contradictions. Hilbert's grand plan even had a name, formalism. And the goal? Well, it was to build a kind of logical fortress. The idea was that inside this fortress, every single mathematical statement you could possibly think of could be proven, without a doubt, as either true or false, just by following a set of rules. No gray areas, no paradoxes, no nagging unanswered questions. A perfect little universe of pure logic. And you know what? Hilbert's dream of a perfect system actually seemed like it was within reach. But then, a quiet, almost unknown genius stepped onto the scene, and, well, he dropped an intellectual bombshell that changed the game forever. That genius was Kurt Gödel. And look, if Hilbert was the great optimist, Gödel was the profound realist. He wasn't some kind of rebel trying to tear everything down. Nope, he was just trying to see things exactly as they were. And what he discovered? It was just astonishing. And this right here, this is the incredible clash of ideas. On one side, you've got Hilbert's ambition for a perfect, complete system, and on the other, Gödel's mind-blowing discovery that any system like that is, by its very nature, incomplete. Hilbert wanted a system with no contradictions, but Gödel proved that a system couldn't even prove its own consistency. And the biggest shocker? The goal was to prove every statement, but Gödel showed there will always be true statements that are just impossible to prove. Okay, I know, this sounds pretty devastating, right? Like logic itself just snapped in half. But honestly, that's not the right way to see it at all. To really get what Gödel was saying, we've got to go a little deeper. So here's the absolute heart of it. Gödel's first incompleteness theorem basically says that in any consistent logical system, one that's powerful enough to do basic stuff like adding and multiplying, there will always be statements that are true, but that you can't prove are true using the rules of that system. It's a fundamental limit baked right into logic itself. So the big question, the one a lot of people jump to, is this. Did Gödel just ruin math? Did he take this perfect world of certainty and just shatter it into a million pieces? I mean, is that what happened here? No way. Absolutely not. And this lays it out perfectly. The myth is that Gödel ruined math. The reality is that he just revealed its natural built-in limits. And result is that math is still totally rational, it's still reliable, it just isn't all-powerful. It can't explain everything, and that includes explaining itself completely. And honestly, this is where the whole story gets really beautiful. Because once you get over that initial shock, you start to realize that Gödel didn't slam a door shut. He actually threw open a window to a much, much bigger and more mysterious universe of truth. What Gödel really showed us is that any formal system we humans can create, no matter how brilliant it is, has this inherent blind spot, a kind of hole in its logic. There are always going to be truths that exist just outside the reach of that system's rules. Which brings us to what might be the single most important takeaway from all of this. Truth and proof, they are not the same thing. Proof is a tool, an incredibly powerful tool, for finding out what's true. But the landscape of truth itself is infinitely bigger than what we can ever hope to formally prove. So Gödel's discovery doesn't really leave us lost in uncertainty. It leaves us in a state of wonder. It makes us ask, if our most powerful system of logic has limits, what other tools do we have in our search for truth? What about intuition, creativity, or just plain observation? And it leaves you wondering, What other incredible truths are still out there, just waiting for us to find them?
You know, we tend to think of mathematics as this perfect logical fortress. It's precise, it's clean, it's supposed to be perfect. But what if I told you that this perfect system has a fundamental leak, a hole in its own logic, that at its very core, there's something missing that it can never, ever explain about itself? Let's dive in. So, this is the big question, right? How can a system built on pure cold reason have these built-in blind spots? It feels like a total contradiction. But by the end of this, you're going to see that it's not only logical, it's completely inevitable. To get to the bottom of this, we can't just use more math. That's like trying to see the outside of your house by only walking through the rooms inside. Nope. We have to take a step back and look at the entire system from the outside. The tool for this is what our source material calls meta-reasoning. Think of it like putting on a pair of philosophical glasses to see the whole picture. So what is this meta-reasoning really? Well, it's the idea that you can't truly understand the limits of a game by only playing it. You got to step away and actually read the rulebook, maybe even talk to the game designer. Meta-reasoning is our way of reading the rulebook for math itself, looking at its structure, not just doing the sum.
And here it is. This is the key that unlocks the entire puzzle. The source introduces this really powerful distinction between two kinds of cause and effect, the absolute and the relative. I'm telling you, once you get this difference, everything else just clicks into place. Let's make this super simple. Think about a video game. All the characters, the items, the physics inside that game, that's all relative cause. They all follow the rules of the game's code. But the absolute cause? Well, that's the programmer who wrote the code in the first place. The programmer exists completely outside the game and literally created its reality. The characters inside that game could never, ever understand the programmer using the logic of their world. It's just not possible.
And this quote just nails it. The game can never contain or fully explain its programmer. The rules inside the system just can't account for the source of those very rules. The creation simply cannot wrap or contain its own creator. So the big takeaway here is that the source of any system has to, by definition, be outside of it.
Okay, so how does this whole idea of an absolute and a relative cause solve our original mystery about math? This is where it all snaps together.
And here's the payoff. First up, incompleteness. Any system, like the set of all numbers, is automatically incomplete because it can't contain its own origin, that absolute cause, the very idea that defines what a number even is. It's missing its own source code. And second, contradiction. So what happens if you try to force that source code into the system? The whole thing breaks? It's like trying to make the programmer a character in their own game who suddenly has to obey the game's physics. It creates a paradox, a contradiction, because the creator can't be bound by the rules of their own creation.
So what's the big takeaway from all this? This isn't just some quirky little feature of numbers. No, it tells us something incredibly profound about the nature of any system of logic, including language itself.
So, according to our source, this is the final verdict. Mathematics isn't broken. It's a language. It's a language that's perfectly designed to describe relationships within the system, the relative world. Its so-called failure only happens when we try to make it do the one thing it was never built for, to explain the reality outside the system, the absolute. So why does this matter? Well, it helps us see our most powerful logical tools in the right way. Math is like a perfect wrench. It is absolutely amazing for turning bolts, but you wouldn't use it to drive a nail. Its limits don't make it useless. They actually define its purpose. And understanding those limits, that's not a sign of failure. That's a sign of wisdom. And this all leaves us with a final, really fascinating thought to chew on. If a purely logical system like mathematics has these built-in boundaries, this inability to contain its own source, then what does that say about our own tool for understanding the world, our mind? What absolute truths might exist just beyond the reach of our own reasoning?